Hi everyone, I'm Dan Fullerton, and today we're going to talk about ideal gases. Now, our objectives are going to be to identify the key assumptions of an ideal gas, to solve for pressure, volume, temperature, and quantity of an ideal gas using the ideal gas law, and finally to explore the relationship between the root mean square velocity and the temperature of a gas. All right, ideal gases are theoretical models of real gases under the following assumptions. The gas is comprised of many particles moving randomly in a container. Secondly, the particles are, on average, far apart from each other. It's definitely in a gaseous state. And finally, the particles do not exert forces upon one another except for when they come in contact in an elastic collision. That means we're going to neglect things like the gravitational attraction between the particles. So, the ideal gas law relates the pressure, volume, number of particles, and temperature of an ideal gas in a single equation. And you can find this written in a number of different ways. You probably have seen it before as pressure times volume equals nRT, PV equals nRT, or sometimes PV equals capital N times Boltzmann's constant times the temperature. Now, in this equation, capital P is pressure in pascals, capital V is volume in cubic meters, little n is the number of moles of a gas. And really what that is the number of molecules, capital N, divided by Avogadro's number, 6.02 times 10 to the 23rd units, particles, molecules, atoms, whatever it is, per mole. R is the universal gas constant, 8.31 joules per mole Kelvin. T is the temperature in kelvins. And we said already, number of molecules. And Kb is Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin. Now, another thing that's useful to know sometimes is that 1 mole at standard temperature and pressure occupies a volume of about 24 liters. Just a nice thing to know in general. So let's take a look at a sample problem here. How many moles of an ideal gas are equivalent to 6 times 10 to the 24 molecules? Well, the way I would do that is I'd start by writing that I have 6 times 10 to the 24 molecules. That's over 1, and I'm going to multiply it by 1. In this case, I'm going to write 1 as 1 mole is equal to 6.02 times 10 to the 23rd, whatever it happens to be, molecules, in this case, per mole. Molecules will make a ratio of 1, and I end up with right about 10 moles. All right, going a little further. Let's figure out how many moles of gas are present in a 0.3 cubic meter bottle of carbon dioxide held at a temperature of 320 Kelvin and a pressure of 1 million pascals. Well, to do this, I'm going to utilize the ideal gas law. PV equals nRT. And I'm solving for moles of gas, so I'm going to rearrange this to get N all by itself, my number of moles. That will be PV divided by RT, which is 10 to the 6 pascals, 1 million pascals, times our volume, 0.3 cubic meters, divided by the gas constant, 8.31 joules per mole Kelvin, times our temperature in Kelvin, 320 K, gives us about 113 moles. Great. Let's try another problem here. A cubic meter of carbon dioxide gas at room temperature, 300 K, and atmospheric pressure, 101,325 pascals, is compressed into a volume of 0.1 cubic meter and held at a temperature of 260 K. What is the pressure of the compressed carbon dioxide? Well, in this case, since the number of moles of gas is constant, we can simplify the ideal gas equation into the combined gas law by setting the initial pressure, volume, and temperature relationship equal to the final pressure, volume, and temperature relationship. Here's how that would work. I would start by rearranging PV equals nRT to say P1 V1 over T1, equals nr. And I can do that because r is a constant and n in this problem is a constant. We're not changing the number of moles of gas. So that must be equal to P2 V2 over T2. Or P1 V1 over T1 equals P2 V2 over T2. And I'm solving for the pressure of the compressed carbon dioxide. That's P2 here that I'm really after. So let's rearrange this to say that P2 equals P1 V1 T2 divided by T1 V2. Now I can substitute in my values. P2 is equal to our pressure 1, that was 1 atmosphere, or 101,325 pascals, times our initial volume, 1.1 cubic meter, or no, 1 cubic meter, times T2, which was 260 K, all divided by our initial temperature, T1, 300 K, times V2, our final volume, which is 0.1 cubic meter. Put all that into my calculator, and I come up with a pressure of about 878,000 pascals. Great. Let's do one more sample problem here. In this problem, we have 1 mole of helium gas placed inside a balloon. What is the pressure inside the balloon when the balloon rises to a point in the atmosphere where the temperature is minus 12 degrees C and the volume of the balloon is 1/4 of a cubic meter? Well, the first thing I notice here is my temperature is in degrees Celsius. That's going to have to be in Kelvin. So let's convert degrees Celsius to Kelvin first. The temperature in Kelvin is going to be the temperature in degrees C plus 273.15, which will be negative 12 plus 273.15, or 261.15 Kelvin. All right, now we can utilize our ideal gas law, PV equals nRT. And this time we're solving for the pressure. So P equals nRT over capital V. We have 1 mole. Our gas constant, 8.31 joules per mole K. Our temperature, 261.15 K, divided by our volume, 0.25 cubic meters. And I end up with a pressure then of about 8,680 pascals. All right. Let's go a little bit further now and talk about the internal energy of a gas. The average kinetic energy of the particles of an ideal gas is given by the equation average kinetic energy is 3/2 times Boltzmann's constant times the temperature in SI units, which is in kelvins. And the total internal energy of the ideal gas can be found by multiplying the average kinetic energy of the particles of the gas by the number of particles that you have. So the total internal energy is your number of particles times average kinetic energy, which, if we know that the total number of particles is the number of moles times Avogadro's number, and the average kinetic energy is 3/2 Boltzmann's constant times temperature, I can combine those together to say that the total internal energy is going to be 3/2 times the number of moles times Avogadro's number times Boltzmann's constant times the temperature. But this Avogadro's number times Boltzmann's constant is the gas constant, capital R. Therefore, I could write this as the internal energy of the gas is going to be equal to 3/2 our number of moles times the gas constant times the temperature. Another form of the equation to get the total internal energy of a gas. All right, let's do a problem with this. Find the internal energy of 5 moles of oxygen at a temperature of 300 Kelvin. Well, our internal energy is 3/2 times our number of moles times our gas constant times our temperature, which will be 3/2 times 5 moles times 8.31 gas constant, times our temperature, 300 K, or about 18.7 kilojoules, 18,700 joules. Great. Let's do another one. What is the temperature of 20 moles of argon with a total internal energy of 100 kilojoules? Well, we'll use our equation for the internal energy of a gas, U equals 3/2 nRT, which implies then that the temperature must be 2 times the internal energy divided by 3, our number of moles, times the gas constant, or 2 times 100,000 joules divided by 3 times the number of moles, 20, times our gas constant, 8.31, which gives us about 401 Kelvin. All right. Moving on, let's talk about the root mean square velocity. The root mean square velocity is the square root of the average velocity squared for all the molecules in the system. It's kind of like an average velocity for molecules or atoms in the system. Not defined quite the same way, but awfully similar. And it's derived from the Maxwell-Boltzmann distribution function, which is a look at a probabilistic distribution of velocities. And as an example down here, we have a graph showing the velocity of the particles in a distribution compared to the number. All of these happen to be at 293.15 Kelvin at room temperature, approximately room temperature. So oxygen, for example, we see we have a distribution here in blue of velocities, where right around 400 meters per second, that looks like we're pretty close to the top velocity, but we have a spread of velocities. It's a distribution. It's not all of the particles at one single velocity. If we go to something like butane here, C4H10 in purple, you can see we have a higher peak and a more compressed distribution. If we go to something like ammonia, NH3, we have a lower peak, a lower count at that peak, but at a higher velocity and a greater distribution of velocities. So that's what we're talking about when we talk about root mean square velocity. Now, how do you calculate root mean square velocity, or VRMS? Well, let's start with our formula for average kinetic energy equals 3/2 times Boltzmann's constant times the temperature. And what I'm going to do is I'm just going to rewrite this a little bit differently. I'm going to say that average kinetic energy is really just going to be the average of our formula for kinetic energy, 1/2 mv squared, and that must equal 3/2 times Boltzmann's constant times the temperature. But knowing that mass over here is constant, if m is constant, then when I can pull out of the average, I can say that that's going to be 1/2 times the mass times the average of the square of my velocity equal to 3/2, oops, not very pretty there, 3/2 times Boltzmann's constant times the temperature, which implies then I'm going to multiply both sides by 2/m in order to move the 1/2 m to the other side. The left-hand side becomes the average of the square of my velocity must equal 3/m times Boltzmann's constant times the temperature. Now, going to make a slight change in notation here. M, the mass, is the mass of the molecule, which is oftentimes written as mu in these equations, the mass of the molecule we're talking about. So if that's the case, what I'm then going to do is I'm going to take the square root of both sides. So on the left-hand side, I'm taking the square root of the average of the square of my velocity. And the right-hand side, I'm going to write as 3 kBt, and instead of m, I'm going to write that as mu. And I have to take the square root of that side as well. All right, if you look at the left-hand side, though, this average of v squared square root, that is the definition of the root mean square velocity. Therefore, we could write this as VRMS, the root mean square velocity, this left-hand side, is equal to 3 Boltzmann's constant times the temperature divided by the mass of our molecule, square root. One way to calculate the root mean square velocity. But we could go even further if we wanted to. We also know that Boltzmann's constant is equal to the gas constant divided by Avogadro's number. Therefore, as we write this, we could rewrite it as Vrms is equal to 3RT over mu times Avogadro's number square root. But going even further, mu times Avogadro's number is just going to be the molar mass, capital M, the molar mass in kilograms per mole. So when we do that, now we have a new equation for the root mean square velocity is equal to 3RT divided by the molar mass square root. So now we have two different equations we can use to help us calculate the root mean square velocity in our Maxwell-Boltzmann probabilistic function of velocities here. So let's take a look at how we could utilize that. The root mean square velocity of the molecules of a 300 K gas is 1,000 meters per second. What is the root mean square velocity of the molecules at 600 K? Well, I could use my equation. Root mean square velocity is equal to 3RT divided by M square root, which means as I look at this, if I double temperature, then I would get a Vrms proportional to square root of 2 times the original velocity, which is equal to square root of 2 times 1,000 meters per second, or 1410 meters per second. I doubled the temperature as I went from 300 K to 600 K, and because this goes up as the square root of temperature, double the temperature, and I get 1410 meters per second. 1.41 is the square root of 2 times 1,000. All right, one way to do that. Let's take a look at another sample problem here. Hydrogen and nitrogen gas are in thermal equilibrium in a closed box. Compare the root mean square velocities of the molecules. Again, we'll use the relationship. The root mean square velocity is equal to square root of 3RT divided by the molar mass. Now, as we look at this, the molar mass of hydrogen is going to be 2, and the molar mass of nitrogen, since it's diatomic, is going to be 28. So that means we have a 14 times difference, 14x difference in their molar masses. Well, the way I could do this then is because they are related to the square root of 1 divided by the molar mass, I could take the ratio, square root of 1 over the molar mass of hydrogen, divided by the square root of 1 over the molar mass of nitrogen, and I come up with a ratio of 3.74. That means that the root mean square velocity of hydrogen is going to be 3.74 times larger than the root mean square velocity of nitrogen. So we found that ratio without having to go through and calculate all these things because we understand the relationship between root mean square velocity and molar mass. Let's take a look at another one. The temperature of an ideal gas is doubled. What happens to its internal energy? Remember, internal energy is 3/2 nRT. So if we double our temperature, we must double our internal energy. So the answer, internal energy doubles. All right. Hopefully that gets you a good start on the ideal gas law as you study gases and thermal physics. If you need more help or looking for more information, check out aplusphysics.com. Thanks for your time, everyone, and make it a great day.